Okay, so next in the document we have a section about multiple integrals, and actually we're not really going to work really on that topic, actually not now anyway. So maybe just a reminder about the Fubini theorem, so that the one that expresses that if you've got an integrable function of two variables, then you can exchange the order of integration, but only if we have continuity, okay, and that's pretty important. And you are given here a counterexample, and I'm sorry, there was a typo, so you should correct this, because, well, if you keep these bounds, it's just going to work perfectly. And by the way, because it's continuous. But let's take a point where the function is not continuous. So obviously, in 0, it's not defined. For 0, 0, it's not defined, and you can try with polar coordinates to show that it's not going to be a continuous, this one is not going to be a continuous function in 0. And now if you perform the integration between -1 and +1, okay, for both variables, you will see that in one case you get pi, and in the other case you get negative pi, okay? So if you just want to give it a try, that's always interesting. Okay, so Fubini, that's old story, you know this. And just a quick reminder of the formula where you want to apply a substitution for functions with n variables. You still have to plug the absolute value of the Jacobian in the substitution in order to make it work. Okay, so this being said, let's go to the next section. So it's called LP of R spaces, and well, let's talk about this in a bit more details than what you have on this document. Okay, so LP spaces and more. Don't worry, it's going to be quite abstract because it's really the foundations of a lot of math theories that were established at the beginning of the century. So it may not be on this kind of thing that I'm going to evaluate you on, but I would really like you to follow the story because it's really some very nice ideas, and it's really also the continuation in terms of theories of what we saw last year in linear algebra. Okay, and if you remember the pre-Hilbertian spaces that we talked about, that was the vector spaces that had an inner product. The other name for this kind of spaces was pre-Hilbertian. Okay, this year we're going to see what's called Hilbertian spaces. Okay, that's going to be a space that is called L2 of R. And in general, you will, well, I will show you, so L2 of R is a very important space. It's going to be the good space where a lot of things work exactly like if you were in a usual vector space. That's a very nice property. But we are also going to speak at least quickly about what's called the LP spaces, which are Banach spaces, and even Sobolev spaces. Okay, I'm just giving you the names because they are the names of some very, very important mathematicians at the turn of the century. So, and they really built the foundations of modern mathematics, as I say. Okay, so let's go back to things that we can easily represent. R2, the plane, right? So in R2, the good thing is that you can calculate distances. What do you use? You use the norm, okay? The norm, and the norm of, let's say, if that's your point M with coordinates x, y, and you want to compute the distance between the origin and your point, well, you very well know that you can apply the Pythagorean theorem, and that's just this distance OM you can subscript that with a little 2. OM is just going to be given by the square root of x2 plus y2. Okay, so that's things you've known for quite some time now. And in R2, using this distance, if you want to draw the unit ball, what is that? The unit circle, it's going to be the points that are at distance 1 from the origin, so unit circle. So as it says, as you get its name, you get that it's going to look like a circle. Okay, but you can really define many more distances, and I think this is something you were shown year 1 when you were introduced to functions of several variables. Some other distances that we can define, you can have, sorry about the thickness, so let's make it less thick. The distance 1, the L1 distance, what would that be? That would be just summing the absolute values of the coordinates. Okay, and in that case, what would the unit circle look like with this knob? Of course, this point is going to belong to it. This one is also going to belong to it also. But then, for instance, the point that has 1/2 is going to belong to it, and a lot of, well, others in between. So actually it makes just a line, right, like this, so that every time you've got a value, it's going to be completed by the corresponding y value. So unit circle with norm 1 is that's kind of diamond. Okay, unit circle with norm 1. This is also called that's also called the Manhattan distance. But this is some norm that is used for some computer applications, and sometimes it has some very interesting properties. Especially as I've seen that recently in data science, in machine learning, some people prefer, well, for some applications, you will tend to rather use this kind of norm rather than the L2 norm, which is, again, what is natural with the 2 norm, with the norm with the subscript 2, is that it just looks like the usual geometry. That's the Euclidean geometry, that's the usual distance. Okay, so that's the most natural one. And again, you know what, maybe some nice property of this norm is that it comes from the scalar product. Okay, so that comes also from an inner product, right? And that makes it a very convenient one to work. The angles are well defined, because you can define the orthogonality with some other norms like the L1 norm, so you can call it the L1 norm with a small l. That was the L2 norm. Okay, usually the small l is used for items in Rn, while the big ones that we're going to use a bit later on are used for functions, but whatever. So you've got the 1 norm. You can even define some other norms. You can define the LP norms. Okay, very similar to what we are going to do. So what would you, sorry, with the subscript p, well, instead of squares, you're going to take power p's. So that's going to be xp plus yp, so all these with absolute values. And then you take the pth root of this value. And the highest p gets, the closest it's going to be to some kind of square. Okay, so something like this with norm p, with norm of LP. And then you have, in the end, you've got the L infinite norm. So you can write the subscript either as a subscript or an upperscript. Okay, depends on the notations you use. Okay, some people use. Okay, the infinite norm It's just going to be you take the maximum between the two absolute values. And for this, the unit circle is just going to be the square. Okay, maybe you can take a few seconds to pause and think about why it looks like this. Okay, so again, in some applications, it has its importance. Okay, idea is, can we do the same kind of thing with functions? Because, well, you've learned a lot of algebra last year, and you've seen that the R2 space or even the any Rn space, they are what we call vector space. Okay, so they have this nice linearity property, linear space, vector space. They have this nice property, and we could even build more properties for spaces with where we could define an inner product. Okay, so an inner product, scalar product, so the same thing. That we can use this notation. You remember I like this notation because then you see really nicely what it gives you, and that's why. Okay, and we could again, sorry, define the so in Rn we could define the if you've got x in Rn, that is would be given by x is equal to x1 up to xn. Its usual L2 norm coming from the inner product is, so the square is given by the inner product of x with itself, and as you know, the inner product that we define usually, well, you could find some other, but the inner product that we define in Rn is just the dot product, so it's really x dot x, or if you want to use usual matrix multiplication, x transpose times x, and that's just going to be the sum of the xi square. Okay, from 1 I is equal to 1 to n. Okay, so this is a lot of things that we saw last year. Now we're going to go to spaces of functions, so which are going to be infinite dimensional spaces. Okay, so spaces of functions, and we worked a bit on this last year. There are a lot of things that a lot of exercises in most of the worksheets we did last year. I tried to introduce also some exercises about infinite dimensional spaces. Okay, so and here we go. Let's go to the LP spaces. Okay, L to the P spaces, and as we happen to work with functions with only one variable and one real variable, let's call them LP of R.